Welcome to the ePathshala lecture series in computer science. We are dealing with the computer architecture course. So, this module is on the design of the memory hierarchy. So, the objectives of this module are to discuss about the need first of all for a hierarchical memory system and also discuss about the different types of memories and their characteristics. So, whenever we look at memory modules, what is it that we want from memory modules? We always want to have fast memories. We also want the memories to be very large, so that we are able to store lots of information in memories, and these memories should also be affordable. So, we want all this together. We want the memories to be fast, we want them to be large, and we also want them to be cheap. Now, all this does not come together. You can't have all these features in any particular memory. So, what is the solution to it? So, the solution to it is organizing the memory system into a hierarchy. So, we go into a hierarchical memory system where each one of the memories in each level of hierarchy satisfies some requirement. So, the entire addressable memory space is available in the largest and the slowest memory, which is the outermost memory, and then you have incrementally smaller and faster memories, each containing a subset of the memory below it as you proceed towards the processor. So, the memory that is closest to the processor is going to be the fastest, so that it is able to supply the processor with the data at least on par with the to some extent on par with the processor, and your capacity requirements and all that are satisfied as we move away from the processor. Now, why does this hierarchical memory design actually work? What if we have different types of memories at different levels of hierarchy, and we say that we are going to store only a portion of the data in this fastest memory, because it is only a small memory, it cannot accommodate too much of information. Now, how is this going to be effective? This is basically effective because we know that most of our programs follow what is called the principle of locality. Now, what do you mean by principle of locality? Principle of locality indicates that a program accesses a relatively very small portion of the address space at any instant of time. We say that the processor spends 90% of the time only on 10% of the code. So, it is only a portion of the memory which is going to be addressed again and again. So, based on this principle of locality, we find that a hierarchical memory system will work. There are two different types of principles of locality. One is with respect to time, which is called the temporal locality of reference. The other one is called the spatial locality of reference. When you look at the temporal locality of reference, it is basically locality in time. That is, if an item is referenced by the processor now, it is quite likely that the processor will again reference it in the near future. Soon, it will reference it soon. So, examples are loops which get reused again and again. The second type of locality is the spatial locality, where it is locality in space. Most of the cases we follow only a straight line sequencing of instructions or a straight line code, and we look at an array axis where one element of the array is accessed now, and then the next element of the array is accessed. So, in such case we come to the conclusion that if one item is referenced, then it is quite likely that the next item in the next address is going to be referenced soon by the processor. This is called the spatial locality of reference. And because programs exhibit both temporal locality of reference and spatial locality of reference, this reference of locality or locality of reference can be exploited by the hierarchical memory system. And for the past 15 years, the hardware has been exploiting this locality of reference, and it has relied on this locality of reference for speed. So, the temporal as well as the spatial locality of reference ensures that nearly all references can be found in smaller memories. So, even though we are not able to accommodate the entire program in the first level of memory, which is closest to the processor, in spite of that fact, because of the temporal and spatial locality of reference existing in these programs, we are able to give the references to the processor, and most of it is found in these memories itself. Now, this gives us an illusion of a large fast memory being presented to the processor. So, this is an example of the hierarchical memory system. We have two hierarchies shown here. One is a memory hierarchy for the server, and the other one is a memory hierarchy for a personal mobile device, a PMD. So, the sizes are shown. So, the innermost level is the registers, where the registers are part of the processor, and that is the fastest memory that you are talking about. Then you have the L1 cache, you have the L2 cache, you may also have an L3 cache. So, multiple levels of caches, and then you have your main memory, and then finally you have your secondary storage, say your disk storage. So, all this forms the memory hierarchy. When you are looking at a PMD, you may not have 3 levels of caches, maybe 2 levels of caches. So, you have the registers as the innermost memory, then you have level 1 cache, level 2 cache, and then the primary memory, and of course, your secondary storage devices. Now, below that are shown the sizes that we normally talk about when we are trying to access these memories at different levels. So, when you are talking about registers, normally we talk about transfers happening in terms of bytes, and the capacity of the registers will normally be, depending upon the number of registers you have, a few thousands of bytes. When you go to the L1 cache typical values are, say for example, it may be a 64 KB with an access time of about 1 nanosecond. If you look at registers, it is only about 300 picoseconds. When you move on to L2 cache, you find that the size has considerably increased, say typically from 64 KB to 256 KB. The access times have also increased, it is about a few tens of nanoseconds. And then you have the L3 cache, which again increases in size from 256 KB, it has moved on to a few megabytes of data, and the access times have also increased from about 10 nanoseconds, it has moved on to a few tens of nanoseconds. And when you come to the main memory, the size is considerably large, we are talking in terms of gigabytes of storage these days, and it is hundreds of nanoseconds. And disk storage, of course, you talk about TBs of storage these days, and the access time is in terms of milliseconds. The same thing holds good if you are looking at a personal mobile device also. The only difference that can be pointed out in the case of a personal mobile device is, if you look at the secondary storage here, flash memory devices are very common as secondary storage devices when you look at PMDs. So, what we learn from this memory hierarchy is, you can look at different levels or layers of memory, and the one that is closest to the processor is going to satisfy your speed requirements. It is going to be the fastest memory, and because it is fast, it is also more expensive. So, you can't afford to have large sizes of these available. As you move away from the processor, the capacity requirements are going to be satisfied by larger and larger memories, and they are also going to be cheaper. And all this memory hierarchy design, we will always have to keep in mind the fact that though there has been a lot of improvements happening in the memory technology also, the processors performance of processors have been growing tremendously, and the memories also have been growing, performance of memories have also been growing, but the memory improvement in memories have really not kept up with the processor speeds. So, we still find a lot of gap between the performance of the processor and performance of memory, and this speed gap should not be visible when you are executing a program. That is, a processor should not be stalled for memory accesses because of the slowness of the memory devices. So, we will have to look at techniques which will try to optimize the memory accesses, and or at least try to hide the latency associated with the memory access. So, we will discuss about all this as we proceed. So, when you look at the memory hierarchy design, it becomes very crucial, particularly with the recent multi-core processors. With multi-core processors, you know, there are multiple processors on the or cores on the same die, and all these cores are trying to access your memory. So, the aggregate peak bandwidth grows with the number of cores. As you keep increasing the number of cores, the bandwidth requirement is going to increase. So, for example, if you look at Intel Core i7, it can generate 2 references per core per clock, and if you are looking at 4 cores, assume they are working at 3.2 gigahertz, which leads to about 25.6 billion 64-bit data references per second and 12.8 billion 128-bit instruction references. So, this works out to about 409 gigabytes per second. So, that is the bandwidth requirement if you are looking at 4 cores and you are assuming that the cores are operating at 3.2 gigahertz. But what is available today for your DRAM bandwidth is only 6% of this total bandwidth requirement, which is about 25 gigabytes per second. So, that indicates the difference in or disparity between the memory systems and the processor. So, we need different optimizations to be performed on memory devices, like multi-porting the memory devices. So, you have multi-ported memory. You look at pipelined caches so that the cache access can be pipelined. You may look at multiple levels of caches per core, and you can also look at a third level cache which is normally shared on the chip. The other thing that you will also have to look at is not worry only about the performance, but also worry about the power requirements or power consumed by these memory devices. So, when you go in for high-end processors normally have about at least 10 MB of memory on chip as cache. So, this consumes a large amount of area and the power also considerably increases. So, with those basics, we will try to look at the different types of memories that are available. So, basically you can classify memories depending on different characteristics. Now, depending upon the access patterns, they can be classified as, one classification is random access memory. So, random is good, that is the access time is the same for all locations. So, irrespective of which memory address will have to be accessed, you find that the access time is the same. Those are examples of random access memories. So, now random access memories basically come in as two different categories. One is a dynamic random access memory, the other one is a static random access memory. So, in the case of dynamic random access memory, what happens is it is called dynamic because it has to be refreshed regularly. The content that it stores gets destroyed, the charge dissipates. So, you will have to keep writing into it again and again. So, it will have to be refreshed regularly. So, that is why it is called dynamic random access memory. The characteristics of dynamic random access memory are that its densities are very high, the power consumption is very low, it is very cheap, relatively cheap compared to your static random access memories, but it is also slow. So, these are some of the characteristics of your DRAM. On the other hand, if you look at the other type of random access memory, which is your static random access memory, in this case static random access memory, one main difference is that the content will last forever. It is not dynamic. So, as long as power is being applied to these memories, it will store the information that is given to it. So, it is static. It is very expensive, it consumes a lot of power, it is very fast, but the densities are very low. So, naturally we look at SRAMs which are very fast, but do not have too much of density to come in the first level of memory, and as you move away you try to look at having dynamic RAMs. So, the second category is not so random access technology, in which case the access time varies from location to location and from time to time. Examples are your disk access or your CD-ROM access, because you will have to rotate the disk, you will have to bring the read write head under the sector that you have to read from has to be brought under the read write head, and then you will have to read the data or write into the disk. So, the access time varies from location to location. So, that is not so random access memory. The second one is the third type of category is sequential access technology, where the access time is linear in location. So, as you can have an example of a magnetic tape, obviously the access time depends upon the place where the data is stored, because it is linear. You will have to move across the earlier data and then access the data that is required. So, obviously dynamic RAM is used for main memory because it is going to satisfy more of your capacity requirements, but it may not be very fast, and static RAM is going to be used for satisfying your speed requirements. It is used for your caches. So, we look at little more details of these types of memories. So, if you look at a static RAM, the basic cell of a static RAM is shown in this figure. As you can see, you have 6 transistors making up one cell of a static RAM. you have a cross coupled connection here. These 6 transistors in a cross connected fashion are able to store 1 bit of information. This generally provides regular and inverted outputs. It is normally implemented in a CMOS process. It requires very low power to retain the bit. But as you can see, because you have 6 transistors making up one basic cell, it consumes space, and that is why your density requirements, they are not being satisfied by your SRAM. It consumes more space. So, obviously, you can accommodate only less number of basic cells in a given area. This slide gives you the typical SRAM organization. Just for clarity purposes, I have just shown a very small word, small size of memory. So, you have 16 words of 4 bits each. So, depending upon the capacity, you can just increase this to how many ever words you want, and the word length also can be anything. For an example that has been shown here, where you assume that a word is made up of 4 bits and you have 16 words. So, as you can see, there are 16 into 4, 64 cells shown here. So, you 16 words, each one of these words is selected by means of a word selector. So, you have the address, your 4-bit address. To select a 16 words, one of the 16 words, you need 4 bits of address. So, the 4 bits of address indicated as A0, A1, A2, A3 are given to an address decoder, and the output of the address decoder goes to your word select lines. So, if your address is 0000, then the decoder output becomes high for word 0. So, the word 0 is selected. So, you find that all the 4 bits which constitute word 0, all of them get their select inputs high. So, all those 4 bits are getting selected. So, if you want to perform a read operation or a write operation, the appropriate address has to be given and the word has to be selected for a read or a write operation. If it is a write operation that you have to perform, you can see the write drivers that have been shown and the data lines that have been shown. So, all the 4 data inputs D0, D1, D2, D3 will have to be given, and the write enable signal will have to be activated. So, the 4-bit data is written into that particular word. Though all the write enable is applied to all the cells here, you find that the word select signal distinguishes the word that is actually being addressed from the remaining words. Say if it is an address 0000, only word 0 gets selected, the other words do not get selected. So, the information that is written on your data lines, transmitted on the data lines, goes only to that particular word. Similarly, when you want to perform a read operation, the address is again given, one of the words gets selected for a read operation, and you can see the sense amplifiers that have been shown here. So, the sense amplifiers will detect the change, and that will be transmitted as a 0 or a 1 on your data output lines D0 through D out through D3. So, that is the typical organization. If you are looking at bigger size memories, you can just simply expand it. If you look at a DRAM now, unlike an SRAM which was made up of 6 transistors, a DRAM is made up of only a single transistor and a capacitor, and that explains why you are able to have large capacities for dynamic RAM memories, because it consumes very little space. You have only one transistor and a capacitor, but it also has its disadvantages because of the capacitor. Because of the capacitor, the charge tends to leak out. So, you will have to keep refreshing it again and again, and it is also the reading process is destructive, which means that as soon as you read a data, you will also have to write it back. And because of the charge getting dissipated, you need to periodically refresh the DRAM. Typically, at least every 8 milliseconds, you will have to refresh the DRAM. So, this shows you an example of a DRAM cell. So, you can see that compared to your SRAM which had 6 transistors, here you have only one transistor and one capacitor. Now, if you have to do a write operation on this, as usual you will have to select the row line. So, the row select will have to be activated, and you will have to drive the bit line that has been shown here, which will decide whether a 0 or a 1 is to be written into that particular cell. Similarly, for a read, the row is again selected. You will have to pre-charge the bit line to VDD, and here the cell as well as the bit line share charges. Very small voltage changes on the bit line are sensed, and for reading purposes you have a sense amplifier which can detect changes of about 1 million electrons, change in 1 million electrons, and that change is sensed and that gives out a data of 0 or 1. And every time you do a read operation, you will have to write by restoring the value. Similarly, if you have to refresh the DRAM because of the DRAM losing its information periodically, you will have to do a refresh operation. Refresh is just done by means of a dummy read to every cell, because as you do a dummy read, it is followed by a write operation. So, the refresh happens. Now, because of the large capacities of DRAMs, and as you keep increasing the size of DRAMs, and if you look at the organization that we showed for our SRAM, as the number of words increases, your address decoder size becomes very huge. So, normally what happens is, instead of arranging it as a single dimension of cells, it is normally arranged as a two-dimensional array of cells. So, this shows a two-dimensional array of cells, and you have a row selector which comes from the row decoder, and you have a column selector which comes from the column decoder, and only the row and the column, intersection of the row and the column that is selected is going to be the cell that is being selected. So, your address is basically divided into two parts. One is the row address and the other one is the column address. So, the row address goes to the row decoder, the column address goes to the column decoder, and both these lines are activated. As you can see, the blue lines are shown there. So, even though when a row decoder outputs a line, all the cells in that particular row get selected, and when a column decoder is activated, one line of the column decoder is activated, the entire column gets selected, but you find that at the intersection of the row decoder's output and the column decoder's output, there is only one cell available. So, that is the only cell that is chosen for either a read operation or a write operation. So, this is what typically happens in a 2D organization. Now, in order to conserve the number of lines, as I have already mentioned, the capacities are very high, and even though you split it up into two halves, you have a row address and a column address, they may still be too large. So, in order to conserve on the number of lines that are used for addressing, we normally try to look at multiplexing of these address lines. So, you have only one set of lines which will be used for transmitting the row information as well as the column information. So, normally the row information is transmitted along with the row axis strobe, and the column information is transmitted along with the column axis strobe. So, having discussed some of the basic memory types, we will simply recall our Amdahl's law, because Amdahl's law gives us a caution or warning about the optimizations that we will have to use and how effectively we use these optimizations. Because we know that even if we bring in an enhancement to the processor, say for example, you are trying to bring in an enhancement to the processor, the speed up that you get in the overall system is going to be dependent on the time for which the fraction is enhanced. So, which means, say for example, I am trying to bring enhancement to the processor. So, the processor is becoming faster and faster, but the process still has to do some amount of memory access. So, if your memory is not being speeded up, if the speed of the memory or the capacity of the memory does not grow linearly with the processor's requirements, what will happen is the number of memory accesses that you do will try to pull down the processor's performance. So, we will have to look at multiple different optimizations for handling this problem. So, one way of optimizing the DRAM that we showed earlier is trying to look at multiple accesses to the same row. So, you can transmit the same row address strobe and you can perform multiple access to the same row. You can also look at different technologies. Instead of looking at a simple DRAM, you can look at what is called a synchronous DRAM, where you try to add a clock to the DRAM interface and also try to look at a burst mode of operation with a critical word getting transferred first. The other optimization that you can look at is going in for wider interfaces, and another optimization that you can look at is a double data rate DRAM, where data is transferred at double the capacities considered to your normal DRAM. And you can also look at multiple banks on each of these DRAM devices. So, based on the optimizations that have been suggested here, you have different types of DRAMs available. One is a synchronous DRAM. The synchronous DRAM synchronizes itself with the timing of the CPU. So, the memory controller knows when data will be ready and CPU cycles are not wasted. And it also comes in several different speeds depending upon the clock frequency of the processor, so that it can synchronize with different processors. And reducing power in SDRAMs can happen by going in for the lower voltage mode or lower power mode, where you ignore the clock and you continue to refresh. The other types of DRAMs are DDR SDRAM, wherein the synchronous DRAM itself you can look at a double data rate SDRAM, where it transfers data on both edges of the clock, and this obviously doubles the memory chip's data throughput and it consumes less power. So, the other optimizations are, you can look at a Rambus DRAM or you can look at a concurrent Rambus DRAM. All these are extensions of the synchronous DRAMs that were proposed earlier. All these are faster than the DDR SDRAM. They are more expensive. They were basically developed for high bandwidth applications. The Rambus DRAM was basically developed by an intellectual property company located in Los Altos, CA, and this was tied up with Intel for the Pentium 4 motherboards. And then DDR was further extended to DDR2, DDR3 and DDR4. DDR2 characteristics is that it has very low power, about 2.5 volts to 1.8. From 2.5 volts it was reduced to 1.8 volts. It supports higher clock rates. DDR3 gives you again, these are the voltage ranges and the frequency ranges at which it can operate. DDR4 is just 1 to 1.2 volts and it can operate at 1600 megahertz, and of course you have a graphics memory based on DDR3, which is DDR5, GDDR5. So, the characteristics of your graphics memory, it achieves about 2.5 speed up bandwidth per DRAM versus DDR3. It has wider interfaces, it has higher clock rate, possibly because they are attached via soldering instead of your socketed DIMM modules. The other type of memory that we are looking at is a read-only memory, which is programmed at the time of manufacture. So, it cannot be written again and again. It is not erased by loss of power, but some of them can be erased and rewritten by special hardware, examples of EPROMs and EEPROMs. Read-only memories normally look at only one transistor per bit, and they are basically used in the BIOS of desktop computers and also embedded devices which serve as a code protection device. So, the next type of memory that we are looking at is flash memory. Flash memory is again a type of EEPROM, electrically erasable PROM. It must be erased in blocks before being overwritten. It is non-volatile, so it stores the information even when power is removed, and you have limited number of write cycles here. It is cheaper than an SDRAM device, but more expensive than device. It is slower than an SRAM device, but faster than your disk. So, if you look at the terminologies associated with memory hierarchy, we talk about a hit where the data appears in some block in the upper level. So, that is called a hit. The hit rate is the fraction of memory access is found in the upper level, and the hit time is the time taken to access the upper level, which consists of the RAM access time plus the time to determine whether it is a hit or a miss. Now, as against a hit, you also have a miss, where the data needs to be retrieved from a block in the lower level and your miss rate is 1 minus the hit rate. And suppose if it misses in a particular level of memory, then you will have to pay a penalty for it, that is a miss penalty. So, the miss penalty is the time to replace in a block in the upper level and the time to deliver the block to the processor. And obviously, we want the hit time to be far less than the miss penalty. So, if you find a word that is in a particular level of memory, it is called a hit. If it is not available in that particular of memory, it is a miss. For example, if you look at a word in a cache and you find it, it is a hit, otherwise it is a miss. If it is a miss, then you try to access the word from the next level of memory, and you try to, when you access it from a next level of memory, you just do not bring that word alone. Along with that, you bring in a block of data, so that you are trying to exploit the spatial locality of reference. Now, looking at the performance metrics associated with memory, we normally talk about latency, we talk about bandwidth, particularly important when we look at multiprocess and IO, and we look at the access times. Access time is defined as the time between the read request and when the data actually arrives. You put in a read request and when does the actual data arrive. Cycle time is the minimum time that should elapse between two requests to memory. Now, to show you an example of the impact on performance, so this example gives you details of the clock rate, your CPI, original CPI value. It is shown that 50% of the instructions are arithmetic logical instructions, 30% of the instructions are load store, and 20% are control. And assume that 10% of the memory instructions are memory related operations, and they get a 50 cycle mess penalty. So, if you try to look at this data and if you try to calculate the CPI value based on this data, you find that the CPI value is 2.6, which means that 58% of the time the processor is stalled waiting for memory. So, that shows you the importance of how the memory hierarchy design is and how memory can actually pull down the processor speed. And if you look at a 1% instruction miss rate itself, that will add an additional 0.5 cycles to the CPI. So, how is the hierarchy managed? So, normally when you look at the access between registers and memory, it is normally managed by the compiler or the programmer. Between the cache and the memory, it is normally managed by hardware. And if you look at the main memory and the secondary storage devices, your memory and your disk, it is mostly managed by hardware and the operating system by means of virtual memory, which we will discuss as we proceed with the other modules. So, to summarize, we have looked at the need for a hierarchical memory system in order to meet the speed, capacity and cost requirements. And when you look at a hierarchical memory system, we basically try to exploit two types of locality of reference, the temporal locality of reference and the spatial locality of reference. And by taking advantage of the principle of locality, we are trying to present the user with as much memory as is available in the cheapest technology and provide access at the speed offered by the fastest technology. And there are different types of memories which are available, like ROM, flash memories, and different types of DRAMs are also very useful. DRAM is slow but cheap and dense. It is a good choice for presenting the user with a big memory system. SRAM is fast but expensive and not very dense. It is a good choice for providing the user fast access times. Thank you.